Welcome back to AI Paper Podcasts, everyone. Today we're plunging into some really fascinating new research. It gets right to the heart of how well large language models really understand long documents.
Yeah, it's a critical area.
We're dissecting reasoning on Multiple Needles in a Haystack by Yidong Wang. Now, for those of you catching the short version, this paper basically cracks open the idea that just because an LLM can handle a massive amount of text, maybe up to 1 million tokens,
Which is huge.
it doesn't mean it can actually reason deeply within it. The researchers found that as the context length gets longer, the model's ability to, truly reason can actually degrade. And interestingly, this isn't about losing information in the haystack. It seems to be linked more to a kind of shrinking of the model's internal thinking process.
Right, how much work it's doing internally.
Exactly. But the good news, the paper proposes and validates a retrieval reflection approach. It seems like this can significantly mitigate that decline, and it even shows promise in boosting performance on tough math problems.
Yeah, some really interesting side applications too.
Okay, so with that quick overview, let's really dive into the details.
Let's do it. This paper tackles, like you said, a crucial question, especially for anyone pushing the boundaries of what these LLMs can actually do. We've seen these incredible leaps in context window size.
Right, 1 million tokens is almost hard to comprehend.
It really is. It's like throwing an entire novel or more at these models. But the original way we tested their comprehension, that classic needle in a haystack task.
Just finding one little fact.
Yeah, just hiding one fact in all that text. It starts to feel a bit, simplistic, doesn't it? Especially now. It's like testing if someone can find a single word on a page versus, understanding the complex arguments across an entire book.
That's a great way to put it. So, okay, the researchers needed a more rigorous way, something tougher, to evaluate genuine long context understanding. And that's where this multiple needles in a haystack reasoning task comes in, MNIHHR.
Exactly, MNIHHR.
Think of it like this. Instead of just one hidden fact, it uses multi-hop reasoning questions. Okay, so you need multiple pieces to get the answer.
Precisely. These are the kinds of questions where you need to pull together several different pieces of information, the multiple needles, to actually arrive at the correct answer. And the clever part is that each of these crucial pieces is deliberately buried within a much larger, noisy body of text, the haystack.
Right, making it harder to just stumble upon them.
Definitely. And initial studies using this MNIAHR approach started showing this concerning trend as you made the haystack bigger, so longer context.
Accuracy went down.
Accuracy on these reasoning questions actually went down. But those early studies, they didn't really tell us why this was happening, or importantly, what we could do about it.
And this paper really gets into that why, doesn't it? One of the first things they suspected was maybe the models weren't even using the haystack at all.
Right, that they might just be pulling answers from their internal knowledge, their training data.
Yeah, like they've already read the book somewhere else and are just reciting the answer instead of finding it in the text you gave them.
That's a perfect analogy, and it's a real problem for evaluation. So to tackle this, the researchers designed a very clever filtering method.
Okay, how did that work?
Well, they focused specifically on questions where a model could get the answer right if the relevant needles, the supporting documents, were actually present in the context, but crucially would get it wrong if those needles weren't provided. This filtering effectively isolates the cases where the model is truly relying on the provided long context for its reasoning, not just memory.
Okay, so they put on these special context reliance goggles, if you will, filtering out the memory-based answers. What did they see then? The paper has those figures, figure 1 and 2, showing the before and after, and they look pretty dramatic.
They really are. If you look at figure 1, before filtering, you see a decline in accuracy as context length increases, but it's relatively gradual for most models.
Okay.
But then look at figure 2. After filtering out those potential memory-based answers, wow, the picture becomes much starker.
Yeah, it drops off much faster.
Much faster. Across all the models they tested, the big commercial ones like GPT-4o, Claude 3.5 Sonnet, and also the open source players like Llama 3AB Prolong, Qwen, GLM, the accuracy drops much more sharply as the context gets longer.
And there was a difference between the types of models, too.
Yes, that's particularly interesting, especially for our technical audience. If you look closely at the figures, the dashed lines represent the open source models. their accuracy decline after filtering is notably steeper than the solid lines for the commercial models.
Oh, okay.
It suggests there might be a gap in how effectively different architectures are currently leveraging these really long contexts for actual, reasoning versus just retrieval or relying on priors.
That's a really crucial distinction. So it's not just a universal problem hitting all models equally hard. Some seem to struggle more once you force them to use the provided text. Okay, so the big question then, if they're not just memorizing, what is causing this performance dip in these super long contexts? The paper looked into a few possibilities, right?
It did, yeah. A very systematic investigation. First, they checked if the position of the key information mattered, the needles.
Like, is stuff buried deep in the middle harder to find?
Exactly. They used this depth percent metric in Figure 3 to vary where the needles were placed. They also looked at the distance between the different pieces of supporting information, the different needles, that's Figure 4. You might guess that if the clues are spread really far apart in the text, it would be harder for the model to connect them.
Makes intuitive sense.
It does. But surprisingly, they found that neither the specific placement nor the distance between needles seemed to be the main driver of the accuracy drop.
Really? That's not what I would have predicted at all.
Me neither. It seems the models weren't just losing information based on where it was located in the haystack.
Okay, so if it's not about where the information is, then what's the culprit? This is where they get into the idea of thinking process length, right? And this really struck me as the core insight.
Absolutely, I think you're right. This is where it gets really interesting. The researchers hypothesized that as the input context gets incredibly long, the models might actually be dedicating less mental bandwidth, if you will, to processing and reasoning over that entire context.
Like they're getting overwhelmed or cutting corners?
Sort of. To test this, they prompted some models. They specifically looked at Claude 3.5 Sonnet and that Llama 3AB prolonged model to explicitly show their step-by-step reasoning before giving the final answer, like show your work.
Ah, okay. Like a chain of thought prompt.
Exactly. Then they measured the length of this self-generated thought process in tokens, and they tracked how that length changed as they increased the input context length. Think of this thought process as the model's internal scratch pad.
And what did they find? Figures 5 and 6 really illustrate this, don't they?
They do. They found a strong negative correlation. As the input context got longer, the measured length of the model's reasoning process actually decreased.
It got shorter.
Yeah, shorter. Particularly for that Llama 3 model, which, remember, had the really significant accuracy drop after filtering.
Right.
Even Claude 3.5 Sonnet, which did better overall, still showed a similar, though less dramatic, trend. It strongly suggests that when faced with these massive inputs, the models might be cutting their reasoning short, maybe leading to incomplete information retrieval, or maybe failing to fully synthesize the connections between the different needles.
Wow. So it's almost paradoxical. You give the model more information, but it ends up thinking less deeply about it, or at least showing less work.
It seems that way. It's not that the information is lost in the noise, necessarily,
Yeah.
but maybe the model's internal engine for processing that information gets squeezed or less effective in these very long contexts.
Okay, so they've identified this potential bottleneck, a shorter thinking process correlating with lower accuracy in longer contexts. What do they propose to, fix this?
So they introduced this retrieval reflection mechanism. The basic idea is to make the model's thinking process more explicit and, crucially, iterative.
Okay, break that down.
Instead of trying to just answer the question in one shot, the model first focuses on explicitly retrieving the relevant information, the needles, from the context. Step 1, find the facts.
Right.
Step 2, reason based only on that retrieved information. Then, to make it even more robust, they added a reflection phase for multi-round iterations.
Reflection.
Yeah. So after the initial reasoning step, the model kind of reevaluates its answer and its retrieved info, and then tries to retrieve more or different information in subsequent steps if needed. They tested this iteratively, up to 5 rounds, as you can see in Figure 7, with models like Qwen, Llama 3, Claude, and GPT-4o.
And did this more deliberate, step-by-step, iterative approach actually help? Did it make a difference?
It definitely did. The results they showed on test time scaling indicated that with each additional iteration of retrieval and reflection, the accuracy generally improved. And importantly, the rate at which accuracy declined with longer contexts also decreased.
So it flattened the curve, so to speak.
Exactly. Though, interestingly, they did observe diminishing returns. performance tended to plateau after about 3 iterations.
Okay, that makes sense. You probably can't just keep iterating forever and expect infinite improvement.
Right. There seems to be an optimal number of passes for this kind of process. But the takeaway was that guiding the model to think in these distinct retrieval, then reasoning, then reflection steps is clearly beneficial.
Okay, so that works at test time, prompting the model differently. But they didn't stop there, right? They actually tried to train a model to think this way inherently.
Exactly. Seeing these benefits at inference time, they thought, well, can we bake this in? So they created a fine-tuning data set.
How did they build that?
They took the thinking process, specifically the first 2 rounds of this iterative retrieval and reflection, as demonstrated by GPT-4o. They chose GPT-4o because it had the smallest initial accuracy drop, suggesting its process might be a good template.
Okay, using the best performer as a teacher.
Sort of, yeah. They generated this data for a filtered set of questions. Then they took Llama 3.8b prolonged 64K instruct. Remember, that was the model that showed the most significant accuracy decline originally, and they fine-tuned it using this new process-oriented data.
And the impact of this specialized training. Table 1 shows the results, I think. Was it significant?
Oh, absolutely. It was pretty remarkable. For that Llama 3 model, the accuracy drop when going from a 1K token context up to a 10K context was slashed dramatically. It went from a 25.8% drop in the original model,
Which is quite a lot.
down to just 4.6% after fine-tuning it with this retrieval reflection process data.
Wow, that's a huge improvement.
It really is. And importantly, this method outperformed just directly fine-tuning the model on the final answers alone. It really highlights the power of training models, not just on what the answer is, but how to arrive at it, especially for these complex, long-context reasoning tasks.
That's fascinating. And they even stretched this idea, this retrieval reflection capability, to a completely different domain, math problems.
Yes, which I thought was a really cool extension. They explored whether this framework could help with mathematical reasoning, specifically using problems from the AIME 2024 competition, which are notoriously difficult.
Okay, how did they apply it there? It's not exactly needles in a haystack.
No, it's different. Their approach was quite innovative. First, they had a powerful model, GPT-4o, generate multiple possible intermediate steps or even full potential solutions for these tough math problems, recognizing that many of these generated steps might actually be incorrect.
Right, LLMs aren't perfect at math reasoning yet.
Not yet. So they then used their fine-tuned Llama 3 model, the one trained on retrieval reflection, to essentially sift through GPT-4's generated work and try to extract or identify the correct final answer from that noisy set of potential solutions.
Ah, that's clever. So using the fine-tuned model, almost like a verifier or a smart extractor on the output of the bigger model, what were the results in math then? Table 2 covers this.
Yeah, and the results were quite encouraging. By using the fine-tuned Llama model to effectively pick the right answer out of GPT-4's multiple attempts, they saw a significant boost in GPT-4's pass at 1 score on the AIME 2024 benchmark.
How much of a boost?
It increased from 9.3 up to 15.3. That's a pretty substantial jump on a hard test like A.
Definitely.
It suggests that this iterative retrieval and reasoning framework isn't just a niche solution for the haystack problem, but could have broader implications for improving performance on other really complex reasoning tasks where models might generate intermediate steps.
Okay, so let's try and quickly recap the main takeaways from this deep dive into the paper. It feels like there were several key insights.
For sure.
First, we saw how just looking at raw accuracy can be misleading because of memory-based answers, especially in long contexts. And filtering those out revealed a bigger performance gap, particularly for open source models compared to top commercial ones.
Right, the filtering was key to seeing the real problem.
Second, the reason for that decline wasn't really about where the information was hidden, but seemed strongly linked to this shortening of the model's internal thinking process as the context grew longer.
Yeah, that negative correlation was the big surprise, I think.
And finally, this proposed retrieval reflection mechanism breaking down the process into explicit iterative steps showed real promise. Not just at test time, but especially when used to train models, significantly reducing the accuracy drop and even helping out in challenging math domains.
That's a great summary. This research really pushes us, I think, to think more deeply about how we evaluate long context understanding. It's not just about fitting more tokens in.
Right, scaling the window size isn't the whole story.
Exactly. We need to make sure the models can effectively reason within that huge space. And identifying this thinking process length as a potential factor is, I think, a really valuable contribution.
Absolutely. It really makes you wonder, doesn't it? How might we design future architectures or maybe prompting strategies to specifically encourage more deliberate, sustained reasoning in these super long contexts?
It opens up a lot of questions.
Could we even start looking at new ways to measure model quality? Not just final accuracy, but maybe the quality or even the length of a model's internal thought process.
It's a fascinating possibility. Perhaps the dynamics of that reasoning process itself could become a critical metric alongside our existing benchmarks. It's definitely something to think about.
Definitely food for thought. So for all of you out there working with these long context models, especially on demanding reasoning tasks, hopefully this paper offers some valuable insights, potential pitfalls to watch out for, but also some promising solutions like this retrieval reflection idea. We'll, of course, include a link to the full paper in the description below so you can dive into all the experimental details yourself. And we'd love to hear your thoughts. What are your experiences with long context reasoning? Let us know in the comments.
Yeah, definitely share your experiences.
Thanks for joining us on AI Paper Podcasts.